Hi, my name's Sam Albert. This is my presentation from the 2023 Spaceflight Mechanics meeting. I want to acknowledge my advisor and co-author, Dr. Hans-Peter Schaub, and the work is titled Relative Motion on Highly Eccentric Atmospheric Entry Trajectories. Okay, so I want to start out with some high-level motivation. So just to introduce the concept, we're talking about relative motion. What we mean by that is we have some chief spacecraft and some other deputy spacecraft. We want to describe the motion of that deputy in terms of this relative position vector rho defined here. That's this, so that the position vector of the deputy is the sum of the position of the chief and this relative position vector. And we'll want to define its time derivative and acceleration as well. Okay, so this is almost always looked at in the Hill frame. And so this is defined here in the diagram on the right. And this is written in terms of the radial position vector or unit vector. The angular momentum vector gives us the third direction, that's h. And then the along track completes the set. And I can only speak for myself, but the intuition that I think of when I hear these labels is I sort of think of radial as being up. I think of a long track as being more or less the direction that I'm going. And then I know that out of plane, the cross track is some direction not in the other two directions. And if you're on a circular orbit, this works extremely well. So here I'm showing the circular orbit. I'm showing the radial and along track vectors, and I'm also showing the velocity vector in red. And you can see, or rather you can't see the along track vector because it's identical to the velocity vector in this case. And on the right, what I'm showing is the relative motion for a lead follower formation. So the deputy is only offset from the chief in terms of the anomaly angle. And for a circular orbit in the Hill frame, this is just a stationary point. So this is great. Now, if we increase that eccentricity up to 0.5, if we look at the diagram on the left, you can see that the along track and the velocity vector are no longer identical, but they're still pointing in pretty close to the same direction, even for this relatively high eccentricity. And then you can see that this lead follower formation, we've now got motion in both the radial and along track directions. So we've got this sort of offset ellipse looking shape. If we increase our eccentricity all the way up to 1.5, now we have motion about a chief orbit that is hyperbolic. And on the left, you can see that this velocity vector is almost aligned with the anti-radial direction. So the along track vector is not even close to pointing in the direction that we're actually going, in the velocity direction. You can also see that our lead follower formation in the Hill frame is becoming a little bit less intuitive. It's still totally physically valid, but it's just a little bit less intuitive to understand what this shape means for something that is as simple as a lead follower formation. What this motivates is, maybe we can consider a different frame and see what things look like there. And specifically, we'll look at the velocity frame. And so in this case, the second unit vector is aligned with the velocity of the chief spacecraft. And so what this ends up meaning is the two frames are offset by flight path angle. And on a circular orbit, flight path angle is 0, and this would be identical to the Hill frame. And I'm also showing here the angular velocity vector and its time derivative between these two frames. So those depend on the time derivatives of the true anomaly angle F and the flight path angle gamma. So if we look again at a lead follower on a hyperbolic orbit, I'm co-plotting here the motion in the Hill frame, which we saw earlier. And then if we look in the velocity frame, there's almost no motion along the x-axis. Almost all motion is just back and forth along that velocity direction. And so I think this is a little more intuitive because in a lead follower, the spacecraft is always, if you're close to it, it's always ahead of you, or it's always behind you. And the distance between you might just be changing. And so, maybe this provides a way of looking at relative motion that is more intuitive in certain cases. So to really take that idea and run with it, in this next section, we're going to take some of the sort of fundamental building blocks of relative motion for Keplerian orbits that are almost always looked at in the Hill frame, and we're going to just derive those same things in the velocity frame. That will involve a fair bit of math that I'll be throwing out. I'll go through it quickly. It's all in the paper. The important thing here is I just want to give you a sense of the different components that come into play. So what we'll do first is look at the relative equations of motion, where our only assumption here is that our chief orbit is Keplerian. And so we're just writing out again this equation with a relative position vector. So x, y, and z are the components of that relative position vector rho, and then xc and yc are the components of that absolute position vector of the chief. So we can take these, take our time derivatives with respect to the velocity frame using transport theorem. So we do that twice, and we can get a kinematic expression for the acceleration vector of our deputy. And so this is the expression we want to manipulate, and it has a number of terms that we want to replace so that there's something we can more easily compute. So we'll start with the second time derivatives of the xc and yc components of the chief position. For this, we can just write a similar kinematic expression for the chief and set it equal to Keplerian acceleration. And so we can rearrange these terms. We'll get our expressions for xc double dot and yc double dot that we can substitute in. Here's that same deputy kinematic expression again. Some of the other terms that appear are, we have all, this coming from our omega term. We've got f dot, gamma dot, f double dot, gamma double dot. F dot is not too bad, but it's not clear what gamma dot and gamma double dot should be. But because we have Keplerian motion and gamma is the flight path angle of the chief specifically, we can actually just use Keplerian orbit identities to develop these closed form expressions to substitute in. And you can see that they are still in terms of f double dot. Oh, right. Alpha and zeta are these dimensionless quantities that I'm just using for notational convenience here. So I'll keep these definitions on screen. And then we also want something for the second time derivative of true anomaly. And we can get that just using conservation of angular momentum for the chief spacecraft. When we take the derivative of h and set it to 0, we can rearrange this expression for the acceleration of true anomaly, so to speak. Finally, we'll take this deputy acceleration and set it equal to the sum of Keplerian acceleration on the deputy and a perturbing acceleration u. That could be control or some, J2, for example. So when we put all of that together, make those substitutions and simplify, these are the relative equations of motion that we get. And to be clear, the only assumption we made is that the chief is Keplerian. So we're not doing any approximations at this point. These equations exactly match just performing the two-body equations for both the chief and deputy. It's just these are written specifically in terms of the components of the relative position and velocity written in the velocity frame of the chief spacecraft. Okay, so we can simplify these a little bit by linearizing about the approximation that the distance between the chief and deputy spacecraft is much smaller than the radius to the chief spacecraft orbit. For many formations, this tends to be a good assumption. So we're linearizing about x, y, and z being 0, and we can get these expressions for, we're sort of replacing the RD cubed term. When you do this for the Hill frame, you can end up uncoupling sort of these x and y terms. Unfortunately, that doesn't occur in the velocity frame, but we'll go through these steps anyway. So you can further approximate by neglecting these quadratic terms, substitute in a useful chief orbit identity, and ultimately what you get is this expression for the linearized relative equations of motion. And so, this is what would be the starting point for something like the CW equations if you were in a circular orbit and if you were in the Hill frame. And so actually these would collapse to that if you evaluated them for a circular orbit, because like I said earlier, the velocity frame and the Hill frame are identical in that case. So these equations don't necessarily lend themselves to analytical solution the way that the Hill frame does for circular orbits. However, it still can be useful for the purposes of onboard control or navigation filters to have a direct way of representing relative motion. That being said, to understand relative motion with these, you do need to numerically propagate these differential equations, which is a bit of a disadvantage. And so an approach that gets around that is writing things in terms of relative orbit elements, where we just compute the Keplerian orbit elements of the deputy and the chief and take the difference between them. And that's what this delta OE represents. And we already have a solution for this in the Hill frame. And in contrast to earlier, where we have these frame-based time derivatives, this is just an analytical expression for the relative position in the Hill frame with respect to these delta R and so forth. And so it's as simple as we know the direction cosine matrix between these two frames as a closed form expression, and we can just pre-multiply the existing solution by that DCM. So in the paper, I go through the full derivation, and I'll also note that the solution I'm showing on the slides here is a more compact version. So you can take orbit identities and substitute them in for things like delta R to get everything in terms of the orbit element differences that we actually want. But and I also could just go through the derivation in more detail to show that this pre-multiplication really does give you the same answer. But all you have to do is pre-multiply by that DCM, and you get these equations for the relative position components of the deputy in terms of the chief orbit elements and the relative orbit elements, such as delta A, delta E. And so you can see that the true anomaly of the chief appears in these equations. So you just sweep through all the true anomaly values of the chief, and at each of those anomaly values, you know the relative position of your deputy. You can notice that this is written in terms of delta mean anomaly. So if we want to look at a hyperbolic chief, we can make some slight modifications to these equations and get a form of them that's very similar, but is written in terms of the change in mean hyperbolic anomaly. So that would be valid for hyperbolic chief. And I'll just make a quick note that you do need to respect the fact that for a hyperbolic chief, its true anomaly must be bounded by these asymptotic values. And if you forget that, the equations will remind you to do so by going singular at those asymptotic values. And then finally, I don't actually show these in the slides, but in the paper, we also take the time derivatives of all 6 of these equations so that for either elliptical or hyperbolic chief, you can also compute the relative velocity based on relative orbit elements. So with all of this, you can analytically compute the full relative state just by knowing the relative orbit elements at any anomaly value for the chief. Some quick numerical examples of this Keplerian motion. So this is, again, our lead follower formation. And you can see, as we saw earlier, almost all of the motion is in the y-axis. And on the x-axis, so the blue is the, just solving the two-body problem for each spacecraft. And the orange dashed line is the relative equations of motion. And as expected, those match exactly. And the actual motion has a little bit of a component along the x-axis. And then when we linearize, that component disappears entirely. So you can see a similar pattern on the right where I'm showing motion in the XY plane. And in this case, I'm also plotting the orbit element difference equations, and those match up with the linearized EOMs. And so it is, as we expected, approximating it as a straight line in this plane, whereas the actual motion is nearly that, but has this little bit of a bend to it. And just to show at least one other case, here there's no anomaly offset, but they're offset a little bit in eccentricity. And you can see that the approximations perform very well for these small offsets. Okay, so everything we've talked about so far has been for a Keplerian chief. But one of the applications that's relevant to these highly elliptical orbits is atmospheric entry trajectories. And we're going to now look at, can we combine the material that we just went through with analytical solutions, analytical approximations for atmospheric flight to make a prediction across the entire mission? So to do that, we'll turn to something called the Allen-Eggers equations. This is an analytical solution to a simplified form of equations of motion for atmospheric entry. The assumptions that we're making are the vehicle has no lift, it has no thrust, and it has constant mass. And so it's mostly defined by this ballistic coefficient, which you can think of as a ratio of the inertial to aerodynamic forces acting on the vehicle. We essentially neglect gravity here because drag is the dominant force. And we assume that the flight path angle is constant. And so in the original formulation, they treat flight path angle as constant at its entry value. In this case, we use something from the literature where you can compute a constant value for flight path angle that's not necessarily its value at entry, that actually results in a more accurate approximation overall. So details are in the paper. Assume a non-rotating planet, and we model atmospheric density as an exponential function of altitude, where capital H is atmospheric scale height. So all of this together gives us a closed form expression for range, and then we can take the first variation of that equation, and the bottom line is we get this expression for the approximate offset in range between the deputy and the chief on the surface based on differences in their radius and flight path angle at entry. So we can now map all the way from a maneuver during approach to a range, offset, and landing. And I'll just very quickly go through sort of a map of how you do that. The entire thing is analytical, but it has a number of different steps. So we start by assuming that a maneuver is defined in the velocity frame and applied to the deputy at this time ti. And between that and the orbit elements of the chief, we can compute the orbit elements of the deputy and get the relative orbit elements. Because we know the radius at entry and the orbit elements of the chief, we can easily compute the true anomaly of the chief at entry. And so between knowing that and the relative orbit elements, we can use the expressions we developed earlier to find the relative state in the velocity frame at entry for the deputy. And we can also, going back to the chief now, we know its orbit elements and we know the true anomaly, so we can compute the position and velocity vectors for the chief at entry. Between these, we can then compute the position and velocity vector of the deputy, so as opposed to relative, the full state. And then we can just do some element conversions and get the difference in radius and the difference in that gamma star. So we compute the gamma star that we want for each one and take the difference. And we can plug that into the Allen-Eggers equations that I showed, and we'll get the predicted difference in range. And I'll quickly note that, this is sort of the predicted difference due to changes, due to differences in their entry state, but they could also be entering at different points on the planet. So in the paper, I explain in a bit more detail how, maybe they have an initial offset in range that's due to these different entry points, and then you can geometrically combine that with the predicted offset in range based on the bearing of each of those offsets, and you get a predicted magnitude and bearing of the final offset in range between where the chief lands and where the deputy lands on the surface. So we set up 3 different scenarios here. The first is based on stardust, so a sample return mission entering Earth on a high-speed hyperbolic orbit, flight path angle of -8.2 degrees, and a relatively low ballistic coefficient. The second scenario is identical except for a somewhat steeper flight path angle. And in the third case, we have a strategic example. So this is a much higher ballistic coefficient vehicle on a high energy suborbital trajectory entering with a steep flight path angle. So the results are shown in this figure, and the same numbers are shown summarized in this table on the left. And for each of those 3 scenarios, we perform a maneuver of 10 meters per second in each of the directions along the velocity frame. So just looking at these in-plane maneuvers, VN and VV, you can see that most of the error we have is coming from the Allen-Eggers approximation, namely the constant flight path angle. And as a result, we see what we'd expect, which is stardust consistently is the worst and strategic is consistently the best, because the steep flight path angle and high ballistic coefficient of the strategic example are a much better fit for the Allen-Eggers approximations than something like stardust, which is relatively shallow and a low ballistic coefficient. And so you can see that the relative, the percent error gets close to 40% for stardust, but for strategic, it's below 5% in both cases. And then finally, for these out-of-plane maneuvers, the percent error is a little misleading because you can look at the actual numbers here and see that the error is always within half a kilometer. It's just that for strategic, the offset is much smaller, so you get a higher percent error. And what's happening here is, in this case, you're maneuvering out of plane, so almost all of your difference in range is just due to a difference in where you initially enter the atmosphere. And so the small amount of error present here is largely coming from rotation of the planet and from error in the Keplerian approximations. I'll quickly go through some conclusions to wrap up. I think we've shown that the velocity frame, it can be an intuitive choice for highly elliptical relative motion. So I think it at least merits, look at your motion in that frame, see what it looks like. We developed the relative equations of motion and the orbit element difference equations, and these both provide these direct relationships in the velocity frame that could be relevant for developing reference trajectories or for potentially onboard GN and C applications. And then we went through an example application of all of this by combining the Keplerian relative models with the Allen-Eggers equations to analytically predict the offset in range on the surface due to a maneuver in the velocity frame during approach. And lastly, I'm just noting that, in this figure, I'm showing percent error with respect to the actual offset in range. But if you take the error of the predicted offset relative to the total range covered by the chief, then all of these errors are below 6% in that case. So at least if you look at it that way, we get a reasonably accurate prediction here, fully analytically using these relative motion models. So with that, if you have any questions, please feel free to email me at the domain on screen. I'd be happy to chat. And thanks for listening.